Okay, get all the technology going here. I've been here quite a few times over the years, so hopefully most of you know me. You won't be afraid to speak up. You got questions, you want to stop and argue with me about something, please holler out, stand up, something. I'd be happy to stop and try to answer your questions as we go along. There's been a lot of attention in the last couple of years about the P index, whether we need a P index or not, what should it look like, do we need to revise what we've had. The P index has been around for 15 years or so now and been in use all across the country. So I'm going to talk a little bit about where we're at today with the P index, what we're trying to accomplish with it, and where we might be going down the road. I don't think I need to tell you guys, what the issue is with phosphorus. It is an essential element. It's not toxic, but it's one of those things, too much of a good thing, really causing eutrophication. When we increase the phosphorus level in the water, that allows excessive algae growth and so forth. And then all the secondary effects we get from that, low oxygen levels when all that algae decomposes and so forth. So I'm not going to belabor that. I think you guys are beyond that. Another thing I think we need to think about when we're looking at the P index is we really got to look at the problem we're trying to solve with nutrients. And we've got to understand that there's really two parts to the problem. One is sort of a systemic issue with nutrients, and this has to do with how our agriculture is structured. And if I can find my mouse, you guys see that? Okay. We have this issue where we're harvesting a lot of crops in places like the Midwest, and then we ship it to the East where we feed it to our animals. And so we can see this is just a map of P balance. Light colors are where we're running a negative balance. Darker colors we're running a positive balance. And you can see, where we're at here on the shore. You can see southeastern Pennsylvania, Shenandoah Valley. You can see a lot of other places, North Carolina, so forth, where there are a lot of animals. We can see where the nutrients are moving from one place to another. The P index doesn't do anything about this. I think that's important to recognize. And one of the things that's been criticized over the years is, well, the P index really doesn't solve the problem. And it doesn't. It helps solve part of the problem, but it doesn't solve the whole problem. And I think that's something important to recognize. The other part of the problem is management. How farmers apply their fertilizer, apply their manure, how much, when, how, all those kind of things. And that is where the P index can really help us out in help guiding that management to minimize some of the environmental effects. This is where most of the effort has gone is in management. Unfortunately, very little has gone into trying to solve the bigger problem, and that's a topic for another time. But I just wanted you to realize that, we're not going to solve the whole problem with the P index. If we look at our watershed here, the Bay watershed, and where the phosphorus is coming from, we have a very big watershed, especially relative to the amount of land or amount of water. This graph up here shows the ratio of the watershed area to water volume, and you can see the Bay has a huge watershed relative to the amount of water. And one of the consequences of that is if we start looking at trying to solve this problem and the losses, we have a lot of watershed where we've got to make change. But actually, I did a quick calculation just taking figures out of the TMDL. And if you take the ag load allocation for the TMDL and divide it by the ag acres they have, it comes out to 0.8 of a pound of phosphorus per acre of ag land. That's what's causing the problem. That makes it difficult, just a little bit, but from a huge area. It's not like it's one big pipe dumping water in or a few big pipes dumping polluted water in. It's a little bit from a lot of different places. And it's not 0.8 from every acre, but that's the average, and it's not distributed evenly. So one of the first things the P index can help us do is help us understand where are those areas that the P is really coming from. What are the high-risk areas? So that's one of the first things that we really use the P index for, is to help us target where we need to worry more about phosphorus and where we can probably put our effort and get more return from that. Another issue that the P index plays a big role in is this localized imbalance. If we take a look here at just comparing the corn crop requirement for NP and K and I use dairy manure. We could do this with any manure. The bars change a little bit, but the concept stays the same. They don't match up very well. The nutrient needs and what we find as available nutrients in the manure don't match. And when we try to put our manure on to supply nutrient needs of the crop, something's going to be out of balance. The most common way we like to do this normally is to apply our manure based on nitrogen. Several reasons for that. Probably the most important one is usually the most economical basis for applying manure, because nitrogen fertilizer is expensive, and if we can use our manure to meet the nitrogen needs of the crop, that saves us from buying a lot of nitrogen fertilizer. Consequence of this, though, is that we do put on, boy, this mouse is, we do put on excess P. And so that's a concern environmentally. What's the fate of that excess P we're applying? The other reason farmers like to do this, frankly, is it allows us to spread more manure. And this kind of goes back to that imbalance I talked about at the beginning. We have a lot of manure in our area of the world, a lot of nutrients we've got to deal with. And so we need to spread as much as we can to try to utilize that. So that's another reason why we tend to go to this nitrogen. Now, if we really wanted to stop the excess, at least on our fields, we could go to a phosphorus-based program where we don't put any excess phosphorus on. That would stop the increase in soil phosphorus, but a couple consequences. One real obvious one here is that we're going to have to buy a bunch of nitrogen fertilizer now because we're only going to meet part of the nitrogen needs of the crop. Second thing is not quite as obvious, but for many farmers is even more important. In this example with dairy manure, we're going to need twice as much land to spread the same manure. And we go to chickens and pigs, it often is even a higher ratio. We need even more land. So this is a difficult choice, and this is one of the places where the P-index comes into play. One of the things it does is helps us decide which one of these is going to be acceptable for us. And really the question is that excess P okay? Can we spread manure on a nitrogen basis, knowing we're going to apply excess P, but be reasonably comfortable that that excess P is not going to be an environmental risk? That's one of the main things the P-index does. If you look at the interpretations on the index, you'll see in most P indices it's N-based, P-based, or none. And so it's helping us to make this particular decision. So that's a very important use for the P-index. Now, the next generation P-index I'm talking about almost wasn't. EPA in particular came out very strong. They thought we should just use soil test. Run either our regular soil test or a soil test that looks at the phosphorus saturation in the soil, but just use that. If the soil test says you need P, you put it on. If it doesn't, you don't. Very simple. From a regulator's point of view, I can see the appeal to that, because it's very simple. You get a number, you hit a certain level, you're done. But it's based on an assumption that really is questionable, and that is that if you're above optimum on a soil test, and I've got a Penn State soil test here, but if you're up here in the above optimum, the assumption is that's polluting. And something we have to recognize about these categories on a normal soil test, below optimum, optimum, above optimum, is that they are based purely on crop response. They don't say anything about environmental risk. And it would be possible that we may even be polluting down here at levels well below what we need to grow a crop. Doesn't tell us anything about that. So making that assumption that just because we're above what a crop needs, we're polluting is not necessarily a valid assumption. We need to, and I'll show you some data here, we need to look at that a little closer. The other thing is we've got to realize is that this can have a huge impact on our agriculture in our part of the world, our animal-based agriculture here. This is just a summary of soil test phosphorus from our lab at Penn State, and just focus down here on the above optimum category, because that's the category that EPA would say no P. Soil test doesn't recommend any, so you can't put any on. 44% of the samples that come through our lab for agronomic crops in Pennsylvania fall in that category. So that means we wouldn't be able to spread manure on, theoretically, 44% of the fields represented by these soil tests. Now, some people would argue that that's the way it is. We shouldn't. Okay? And that is a valid argument. But is it a realistic argument? I think we really have to look at it in the context of our agriculture and so forth. So, and you go some areas, Lancaster County, for example, that's 60%. Lancaster, a couple $2 billion in animal sales in that county, and you're going to basically say you can't spread manure on 60% of the land. Again, it may be a valid argument, but I think we got to step back and really look at, is that something realistic? And so soil test, it has some issues just using a soil test. Now, there is some basis for this. Here's a little bit of research just relating the soil test, Mehlich 3P, to soil loss, P loss, and you can see a pretty good relationship here. So that gives some support to the idea of just using a soil test to predict P loss. Another very important thing this shows is right here. This is the crop optimum. Pennsylvania, we use 30 parts per million as our optimum, and that's what this arrow represents. And you can see at the crop optimum level, we really don't have a big loss of P. We're basically at background levels. So that's very good news. That says, at levels we need to grow crops, we don't have a serious concern with P loss. So we're not going to be limiting farmers' ability to grow a crop to protect the environment based on this data. Normally, we're getting up here in the 150, 200 parts per million or more before we...
Average, or is that
what the average?
is that for corn, or?
This was just a bunch of soils. You mean the optimum? That's the optimum we use for all of our agronomic crops. It's not the same for all, for example, the horticultural crops and so forth. But agronomic crops, 30 parts per million. Yeah. Yeah. No. So, where we start to worry is, we get up in these, get up 150, 200 parts per million. That's where you'll see people starting to, some states using thresholds like that to say, here's where we got to really start worrying about P loss. So there is some basis here for using the soil test, and the argument that if it's above optimum, that by itself is a basis for limitation, I think it is wrong, because you can get, you can get, up in here, you're really not that much higher than background levels, and you can be quite a bit above optimum. So just using that as the criteria, maybe you could make a valid argument if you set a critical level higher, we could use this. Now, note this comment over here. This was just background soil levels, no recent phosphorus additions. We're going to come back to that in a little bit. However, that argued that maybe soil test would work, but here's an example of a landscape when we try to put this out there in the real world. This little watershed in Pennsylvania, there's a hog farm up here, so this watershed gets a lot of manure. Little stream drains the watershed. The ARS group that's located on our campus has done a lot of research in this watershed, and they know the phosphorus pretty much on a first-name basis. And so they've, over a number of years, kind of figured out where the phosphorus is coming from in this watershed that's ending up leaving this little stream. And they've figured out 90% of the P is coming from about 10% of the land area, and it's these red areas. Okay? So that's the problem area. Over here, they did a very high-resolution soil test map of the watershed. And so this is the soil test levels, the low, mediums, and highs in that watershed. And there's some correspondence. Some of these areas up in here, you can see that where loss occurs, they also are high soil test areas. But there's other areas down in here that weren't that high in soil test. And there's a lot of areas here, over in here, up in here, that have high soil tests that we would say would be a high risk for loss, but they really weren't contributing P. So when we put it on a landscape, it doesn't work that well. If we look at individual soils and just look at the runoff and the phosphorus we lose from those, there is a relationship, but you put it out there in the real world, it doesn't work that well. And part of the reason is when we look at any non-point source problem, we've got to look not just at the source, but we've got to look at the transport of that source and what other sources might be contributing. And what we're really concerned with is when you have a source of phosphorus to lose and a way to move it. If we just use soil test, all we're looking at is this one source, the soil. We're not looking at what the effects of adding manure, other than what that does to the soil test, or adding fertilizer, We're not looking at the transport. Is there erosion on the site? Is there runoff? Are we anywhere near water? Those kind of things. So it's not surprising that when we put it on a landscape, it doesn't really work all that well, just using the soil test. This is showing the effect of the different sources. This is that same data I showed you a minute ago for soil, R squared of 0.8 here, but now we've added some triple superphosphate on some sites, some swine manure, some poultry manure, and that's these points up here. They don't really fall in the line. In fact, you could pick a point here somewhere maybe around 150 parts per million in this data, and you go essentially from a background level to the highest loss that was recorded in these experiments, all at the same soil test level. So the soil test really wasn't predicting the loss by itself. It's part of it. But when we have these additions, they become very important. So we can't just look at the one source. The other thing, looking at transport, here's an example of a little watershed, and we have 3 different sites on here where they were monitoring. Here's the soil test levels, 78, 144, 177. If you're into P saturation, 9%, 17%, 21%. So your conclusion based on soil test is that the big loss is here and little loss is down here. When we look at the actual measured loss, though, it was just the opposite. We lost about 8 kilograms per hectare, 8 pounds per acre per year down here, and less than 1 up here. The little stream I should have pointed out is right down here at the bottom. And the reason for that is it's not looking at transport. When you add in the runoff, that's really what dominates in this case, because we had a huge runoff volume down here, 100 times more runoff down here than up here. So when you figure in the transport, now you get a much more reasonable answer, and it matches up with the observation. So just using soil tests without considering transport doesn't do a very good job. We also have to include that transport component. So what this brings us to, and this is really the basis for the P-index, is what we call critical source area management, or figuring out where are the areas where we have an overlap of source and transport. You need both. You've got to have a source of the pollutant you're worried about and a way to move it. And so that's what we're looking for, and that's really what the P-index tries to do. It tries to help us find these red areas on this map, where 90% of the P comes from. Because if we can figure out where that is and maybe change our management there, we can have a lot greater impact than maybe diluting our efforts over the whole watershed. Okay? So it really helps us target, gets the maximum return for our effort. So that's the basis for the P-index to begin with. This is just the Pennsylvania P-index, and it just does that. We have a bunch of source factors, soil tests, fertilizer, manure, when and how they're applied. We have transport, erosion, runoff, leaching, distance. We put those together and come up with an assessment of the risk. Is this an area that's a high risk or a low risk? If it's low, we can maybe use that N-based management. If it's a high risk, maybe we have to go to P. If it's very high risk, we may not be able to put any more phosphorus on. We've got enough risk without adding anything else. So I'm not going to go into the current index in any more detail, just that's where we're at really today. And if you take that, and now this is that same data I've been showing you, but here it's plotted as the P-index, not the soil test P, versus P-loss. And this includes with and without inputs. Now it all does kind of fall on a line. So it tells us when we put these pieces together, we look at all the sources, we look at the transport, we can do a pretty decent job at predicting what that loss might be. So let's look at the evolution of the P-index. The very first P-index, known as the Lemunyon-Gilbert Index, was published, I should have looked at the date, it was in the 90s, I can't remember, 93? Okay. Thank you, Nicole. I knew it was back there somewhere. That was what we called an additive index. They just had a bunch of sources, a bunch of transport, added it all up. You got a big number. It was a high risk, low number, low risk. So that's where it all started. The second generation P-index, one of the main changes went from an additive to multiplicative. And what this did was really captured better this concept of overlap of source and transport. You have high source, high transport, you multiply those together, you get a big number. low source, low transport, you multiply those together, you get a low number. So it's captured this concept a little clearer. So that's where the Pennsylvania P index is now. A lot of P indices are kind of in that second generation. But we've had a number that have been, over the last few years, have been moving to the next generation. And the main structural change to the third generation of P index is what we call a component multiplicative. And what this is rather than taking all the sources, soil tests, fertilizer, manure, adding those up and multiplying them times all the transport factors, we actually break it out by different loss pathways. So we're taking, for example, maybe soil test P times the erosion, because that's the phosphorus that's moved by erosion. We may be taking something like P saturation, which is related to soluble P, times the runoff, and the P saturation times, which is soluble P times leaching. So we're kind of breaking it out into the different pathways, and this is just a very simplified, just to illustrate the concept here. And then we add those up to get the final P index. First off, this is more mechanistic. It actually gets at what's actually happening out there on the landscape, and looks at each one of these pathways. In this approach, any one of these can create a high P index. One of the problems you might have before, you may have high soil test P and high erosion, but you have low runoff. The other factors are low, and it kind of lutes that out. Here, if these were high, that could be enough to create a high P index, because that's the main loss pathway. The other ones really aren't contributing. Now, if you have all of them, obviously it's going to be even higher yet. Also, if we're looking at the different pathways specifically, it allows us to do a better job of targeting our BMPs, because we know in this particular situation, this is the loss we're worried about. This is the pathway that's causing, or this is the source that's causing the problems. So we can target that much more directly with our best management practices. So that's kind of the where we're at today, is looking at this component type phosphorus index. Now, another thing that we've been using this for quite a few years now, and there were a lot of people raising issues about the P index. And this was part of what was behind EPA's move to just go to soil tests. They had a lot of issues with some of what was happening with the P index. And so just wanted to go over what are some of the things that are driving the need to change the P index. The first one, and this is probably the one that got the attention more than any other one really, is the variability in how the P index ratings are interpreted and how we make recommendations. We did comparisons and look at, a single field with a bunch of different P indices and find we get low to very high on the same field, depending on whose index you use. And that doesn't work, okay? So it really came down to, how do we establish these categories? And so what we're really looking at, here's our data again that I've been showing you, and these lines are represent roughly Pennsylvania's interpretation levels for our P index. Low and medium are N-based, high is P-based, very high, can't put any more on. That would be our interpretations in Pennsylvania. And really what we're getting at here, this is kind of a continuous curve, so the question is, where do you draw the lines? It's not like there's a distinct break where this thing goes along and then all at once just goes up in the air. So, you could move it way out there like that, and some states did that. There were some states that had what looked like a very good P index, good relationship between the P index and P loss, but they set their levels so high that it never did anything. You never reached those very high levels, so it was sort of an exercise to make them feel good, I guess, but it really didn't, or make somebody feel good, but it really didn't do any difference. In some places, they've gone to the other extreme, and set them very low, so they're very, very restrictive. And so this is a real problem, is how do we decide where to set this? And the bottom line in a lot of this is it is a judgment call, a value judgment. Do you want to be very protective? Or are you willing to be less protective? Because again, there is no, here's the point. Where it becomes a huge problem. So this has been a big issue, and one of the things that we've had to try to address in moving forward with the P index if it's going to be accepted. The second one is accuracy or poor representation of some conditions. some states have a P index that really just isn't appropriate for their condition. Just a real quick example, a number of years ago, I was invited to give a talk in Denmark. They had a Nordic Countries P Conference, and they wanted me to come and just talk about what we were doing here in the Chesapeake Bay watershed with phosphorus. And then each of the countries there, Finland, Sweden, Norway, all those, somebody got up and talked about what they were doing. And the lady from Norway got up and put her P index up on the screen. It was the Pennsylvania P index. Exact. It was. She had actually spent some time at Penn State with Andrew Sharpley at the ARS lab, and went home and basically, I'm flattered that they used our P index, but I'm just questioning are the conditions in Norway the same as they are in Pennsylvania? Is that really appropriate? Now, that's an extreme example, but even within our states here, and I have a map of the physiographic regions within the Bay watershed. We go from the coastal plain, Piedmont, Ridge and Valley, Allegheny Plateau. All of these are, and so very different conditions across the watershed, and trying to have a single P index that represents all of that, even within a state, can be very difficult. So we really need to look at, can we do a better job of representing the conditions, and should we be breaking this down a little more, not just along straight state lines, but along these physiographic regions. And if you just look at an example here, this is typical P loss. It can leach, it can run off, it can be eroded off. In our upland conditions, like we have in Pennsylvania, runoff and erosion are the dominant factors. That's what drives P loss for us. Leaching is not really a big issue for us. But you come down here on the shore, completely reversed. Runoff and erosion really aren't that important. Now it's leaching. It's this ditched agriculture here, where you have these shallow water tables, phosphorus moving within the soil to the ditches. So we got to be able to capture both of those. And one of the things we have to ask ourselves is, can we do this in a single P index, or do we maybe need different ones for different parts of the watershed? And to me, ideally, and I don't think this would ever work because of politics, but ideally, instead of having maybe 5 or 6 P indices, one for each state in the watershed, we maybe ought to have 5 or 6, but they would represent the different physiographic regions within the watershed across state lines. Like I say, I don't think that'll ever happen, but I think that would make a lot more sense than based on political lines. Another issue that I kind of brought up at the beginning is that people criticize the P index does allow excess P on some fields. And that's true. Remember, we're back here to this idea that we've got an excess in our area. And until we fix that, we're going to have to do something with it. So can we do something with that excess without creating too high an environmental risk? And the other thing is that we've tried to emphasize that the P index is not a P restriction tool necessarily. It's a keep P out of water tool. And one way to keep P out of water is to restrict P, obviously. Don't spread it. That's one option. But there are other ways we can do that. And it was not intended to deal with the excess. In fact, I'll be honest with you, it can make the excess worse because it kind of gives us a little bit of an out. It allows us maybe to spread excess, and that may come back to haunt us down the road. So it kind of says, well, we can go ahead. We don't have to fix this excess problem because the P index says we can spread it. So I think we got to be careful with that. But it does allow excess P. That's a concern. And I think you got to understand what the P index is intended to do. If you understand that and accept that, then that's maybe okay. But we got to understand what the implications are. When we do the excess, we're back to this situation. I showed you the same slide before. We're really trying to answer the question with the P index in a given situation on a given field. Is this okay? Is this excess okay, or do we have to go to a P-based system there? So that's really what we're deciding. Now, that's different than N. N, we've made a decision, and based on a lot of research, that we can't put excess N on. We put excess N on, we know that a lot of that's going to end up in the environment, what the crop doesn't use, so we've said no excess N. P, though, maybe we have a little more flexibility that we can maybe have some excess, but not create too much of an environmental risk. P-index doesn't address non-field application sources of P, you know, these barnyards or cows in the creek or litter sheds, those kind of things. Good example here from down here on the shore, a ditched watershed here, and you can see the different ditches going along. This one really stands out. That happens to be the one that's right here at the upper end of the ditch is the litter shed. And they did a soil test around the litter shed, and over 3,000 parts per million Mehlich 3. So P-index doesn't address that at all. It doesn't do everything. So we still got to deal with these kind of problems separately. A lot of the issues with the P-index weren't so much with the science, they were more implementation. Things like setting those critical levels. Where do we decide to put our cutoff levels, those kind of things. But we have learned a lot, and the science has advanced. And just one example of an area that has really, I think, changed more than any is understanding phosphorus in runoff. Historically, what we've always looked at as soil fertility people is the fact that soil solution phosphorus is very, very low. You know, 0.03 parts per million is kind of a typical soil solution phosphorus level. If we're comparing that, convert that to pounds per acre at field capacity, you know, a couple tenths of a pound per acre, compare that to crop needs, you know, we have a problem. I mean, that's what we focused on for hundreds of years. You know, how can we get high enough phosphorus levels to replenish that soil solution to keep up with crop requirement? So we've kind of built this mentality that P is insoluble, it won't move, it can't be an environmental problem, right? I mean, that's sort of the mindset we had for a long time. But it can be, and what we have to understand is this concept of P saturation. The idea here is the soil has a certain capacity, and our soil is mainly iron and aluminum, to tie up phosphorus. Now there's a huge amount of iron and aluminum can tie up a huge amount of phosphorus. So if we look at the whole soil profile, we might say, yeah, it can't be a real problem because we just have this huge capacity to tie it up. But if we look at what's really happening out there, if we're putting all of our P on the surface, this is just a soil test level with depth, we can build up a very high soil test phosphorus right at the surface, and this can be high enough that it actually uses up most of the iron and aluminum in that thin layer right at the surface. That also happens to be the layer where the runoff is interacting. So we don't have to saturate the whole soil. If we just saturate a thin layer here, now we put more phosphorus there, there's no iron and aluminum to tie it up. It stays soluble. If we have runoff occurring across that surface, we can pick up a lot of soluble P. And that's what this is showing over here on the right, is that as the P saturation goes up, the dissolved P and runoff goes up because it's just not being bound up. So we have to focus on not the whole soil, but on that thin layer up there at the surface. And this just illustrates that, some of Andrew Sharpley's data converting to no-till. You know, we all know no-till is a good practice. A lot of benefits in reducing nutrient loss and so forth, and soil loss. This has sort of been our traditional view, is that when we convert to no-till, one of the big impacts is we reduce erosion and P loss drops. It's true. But in the same set of fields, once we're in that no-till, everything's going on the surface, we can see that saturation building up at the surface, and we can actually see soluble P going up. So we got to understand that it's not just bound up P, but soluble P can be an important component of this. So just an example of something that we've had to change our thinking over the years about how P behaves, and this is one of the areas we're challenged right now in how do we best capture that in a P index. Now, a little story here that relate to current events. I think you're all familiar with Toledo this past summer. Everybody know what happened in Toledo this past summer? They had Western Lake, this is Toledo way out here. Western Lake Erie became very eutrophic. They had these huge algae blooms. They had to shut down the Toledo water system. I don't remember how many million people were in Toledo, but a lot of people, cleaned off the shelves for bottled water. Nobody had water. Big problem. Why did they have that? I think it can teach us some lessons. Basically, if you look at the problem there, back in the 60s, Lake Erie is very eutrophic. They did a lot of work cleaning up sewage treatment plants. That helped a lot. But they also converted a lot of land in Ohio in particular to no-till as a way to cut down on the phosphorus loss going into Lake Erie. Dramatic improvement. Okay? They did reduce the phosphorus loss, reduced the eutrophication. Lake Erie became a much better lake. But one of the things that happened along the way is now that we're in this continuous no-till, we keep putting our fertilizer and manure on the surface. We've built up this layer of saturation there, and this is one of the things driving the problem today is now we've saturated those soils at the surface and we're getting higher levels of phosphorus in the runoff. So we got to understand the whole problem. And I think that's one of the things we've got to look at with the P index. Sort of the lesson here is, yeah, it can it can be very helpful in guiding our management, lowering that environmental risk. But if we just use the P index kind of to maximize P application in the short term, eventually all of our fields are going to have a high P index, and now we're going to be in trouble again. So we really got to think about the big picture, and I think this example of what happened in Ohio is a good lesson for us to kind of think about, you know, if we're going to use the P index, we've got to use it right, and we've got to think about these long-term implications there. I want to finish up just talking a little bit about some of the current efforts, and there is we have a conservation innovation grant here in the Chesapeake Bay watershed. Long title there. Basically, it's trying to come up with the next generation of P index. All the universities and ARS and so forth in the region are working on this. This is part of a bigger national effort. We have one in the Chesapeake Bay watershed. There's one in the middle of the country called the Heartland Project. There's one in the southern region, and also there's sort of a national coordinating effort. There's also efforts in Ohio and Wisconsin that aren't part of this project, but they're kind of doing the same thing. So they're included in this. And the whole idea is really looking at what we need to do to get the next generation of phosphorus index and address some of these challenges and issues that people have brought up. Our Chesapeake Bay objectives are first to try to pull together what monitoring data we have. We have 9 watersheds within the Bay watershed where we have some pretty intensive monitoring that we can use. We've got to then identify what are the conditions and practices that we're worried about that seem to be the ones that are causing the problem, and what are the practices that would best address these. We're trying to evaluate the tools, the P index, by comparing what we get with the index with the monitoring data from these watersheds, but also talk a little bit more about this, maybe using models. You know, we have 9 actual data points in the Chesapeake Bay watershed, 9. That's not very much. Each of these is very, very expensive. These are not something you just go out and, like we put out fertilizer plots or something. These are very large, expensive things to do. So maybe we have to use other tools like models, and I'll look at that here in a minute. And so hopefully we can use our monitoring data, maybe use the models to refine the P index, and then develop the recommendations from the P index, those interpretations linked to management, to BMPs. So that's the objectives of what we're trying to accomplish. And just to kind of talk a little bit about this modeling part, because that concerns people quite a bit. Basically, you know, conceptually ideal, we would have some monitoring sites where we would measure P loss. We could relate that to the P index. We could draw a line through it. And we could say, you know, at this P index, this is the kind of loss we're going to get. That would be great, you know, if we could do that. But again, we only have 9 points to cover the whole watershed. And I already talked about we have 5 physiographic regions. You know, so that's probably challenging to say we're going to get enough data points to really do a good job there. That's where models may come in. In a model, we can take all the conditions, the management, put these in a model and let it estimate what the phosphorus loss is. Much more practical than monitoring because we can do a lot more sites, and I'll show you an example of that here in a second. And we can evaluate many, many more situations. You know, those 9 sites only represent a few sets of conditions, but we can put in different locations, soils, weather, management, topography, put all these different conditions into the model and run a lot of different scenarios and see what the P-loss would be and see how that compares to the P-index. Now, one issue, some people think, well, why don't we just run the model? Why do we need a P-index? Let's just run the model. Well, models are very complex, and I'm not a modeler, but I'm in this project working with modelers, and I had a full head of hair when I started this. They're very complex. It's very frustrating, and trying to get the modelers and people like me getting on the same page. They mean well. I'm not criticizing them, but it's a challenge, and so saying, yeah, we're going to run this on every field as a way to make a management decision is not realistic. Everybody always questions model accuracy, and that's one of the things we're trying to address in this project, is to look at, make sure the models at least capture the data points where we do have actual monitored data. And the bottom line, nobody likes models, particularly us here in the Chesapeake Bay watershed. We all hate the Bay model. Be honest, but it's a reality, and but I think we have to, probably, we're going to have to accept working with something maybe we don't like to work with a whole lot, because I'm not sure what the alternatives are. If we look at the model versus the index, the model can give us an estimate of P-loss. Really, the index is a model. It's just a very simple model where we've taken, some basic factors and put them together, and we come up with an index of phosphorus risk. And we can maybe use the model to kind of correlate those. The model says we have this high P-loss. We'd hope the P-index says this is a high-risk site, and so forth. And we've talked about in the P-index circles, directionally and magnitudinally correct. It's going in the right direction, and the relative magnitude that we pick up in the P-index is related to what's really happening in the real world. It's not designed to tell you you're going to lose 0.8 pounds of phosphorus. It's designed to say you're in a high category or a low category or so forth. So that's one thing we can use the models for in the P-index. The other thing is, because models are built on the mechanisms that control P-loss, we can maybe use the model to look at how we can refine the P-index. What's the relative weighting of these different factors? What are the key factors that we need to have in the index to really give us a good prediction of risk here? So we can use the models to decide, is it going in the right direction? What are our categories? And maybe to refine the P-index and make it more representative of what's going on out there. So if we go back to our monitored situation here, what we can do is now run thousands and thousands of model scenarios. We can put in different conditions, different topography, different methods of manure application, different rates, different weather. We can put all these things in and model that P-loss and relate it to the P-index. Now, we may get something that looks like this. That's not so great. If you look at putting a line through that data, it probably isn't the same line we would have put in just based on the monitored data. And also, we get something like this showing up out here where we've got these points that seem to be outliers. They're saying the P-index is high, but the P-loss by the model is not really that high. Even this one data point, we thought it was just a little bit away from the line, but maybe it was trying to tell us something. So with the model, we can start looking at these things. Well, what's wrong? Why are we missing these points? What's driving this? And maybe then we can look at our index and say, here's how we can maybe modify the index to also capture these points out here more correctly. And hopefully we could put that all together, make refinements to the P-index, and come up with something. This is our goal, would be to have our monitored data, the red points there, and our modeled data kind of fall along the same line. And now we have something we can use with a lot broader confidence. It's not based on just 9 points across the whole watershed, but maybe thousands and thousands of different scenarios. And then if we have a water quality goal, we can set those critical levels. Now we can say, here's where we're going to say it's high. Okay, if we have this kind of data, now we have a much better justification for saying what's high and what's low. It's not quite as much a judgment call. Now, just show you a quick example of this. This is current P-index, Pennsylvania. We take all the sources, all the transport, multiply them together and get the P-index. The component P-index I talked about was you take the different pathways, erosion, runoff, leaching, You take the source for each of those and the transport method, and you get components of the p-index, and then you get a final p-index. I've covered that before. What I want to show you is an actual example using that, where this was done by Carl Bolster, who's a modeler with ARS out in Bowling Green, Kentucky. And Carl was looking at, can we use a model to evaluate and improve a p-index? And lucky for me, he decided to use the Pennsylvania p-index as his test. He wasn't really working on the Pennsylvania index. I don't know why, but he chose ours. That was great because it gave us some free information. So first thing he did was just run our current index here, add up the sources times the sum of the transport, and he related that to his modeled P-loss. And this is 10,000 data points. You know, we can't do 10,000 monitored sites, but he had 10,000 different scenarios. And not bad. I was pleased. I mean, it's R squared 0.52. That's not great, but you know, magnitudinally and directionally, it worked pretty good. So I was pretty happy. The next thing he did then was took our same factors. He didn't add anything else here. He just reorganized it into a component p-index, like I talked about earlier. So he did the sediment, the soluble P for runoff, soluble P for leaching. So he took exactly the same inputs, nothing new here, just reorganized how we calculated it, determined the p-index, and then ran all those through the model and improved it quite a bit. So the point here is, I think it shows how we can use models to look at our p-index and see how well it's doing. We can use the models to maybe improve, and this is where all he did was rearrange things, ran it again, and we see whether it does better. So I think it gives us a good example of the potential for maybe using models to improve the phosphorus index. Back to our project, just want to comment at the end here on this last objective. This is the one that's unique to our project here in the Chesapeake Bay. We're really putting a lot of emphasis on making sure that this is practical and it's going to be effective. We're not just, here are the practices the model says. We're going to look at what are the things that are really going to make a difference, what are the things that are practical to do that are going to make a difference. So we're looking at things like sensitivity analysis. We want to make sure that the things we ask you to collect and put in a p-index really make a difference. Are they the minimum required data? We don't want to put a bunch of stuff in just to make the scientists feel good if it really doesn't change the answer. We want to make sure it's readily available data. We want to make sure we have a better connection to the practices. You don't just get an answer. You got a high p-index, but what are some of the things you need to do now to address that? So kind of make that direct connection. Here we're using stakeholder panels. We've already met across the region, doing surveys of planners and plan reviewers, trying to come up with, you know, what are the kind of practices that we think are effective, what's the practicality. Also looking at making sure it's user-friendly, you know, computer programs. An ideal thing is maybe web-based, where a lot of the information that you have to go out, you know, with a clinometer and get the slope and measure things, and you know, we can maybe do a lot of that with GIS, because we have a lot of that data out there in the cloud that we could probably access and make it much easier for people to run the p-index. These are the main people in the states here that are involved in this. If you're interested in this, you'd like to be involved, you'd like to give input, you know, contact any one of us, and we'd be happy to include you. Josh, you're the question mark there. Always was. Yeah. I don't even want to get into the situation here in Maryland, so I'm not even going to address that at all. Any questions? Herb.
Actually, I do want to get into the situation where we know that, but kind of in a roundabout way. And that has to do with, it seems to me we can get really good at monitoring and predicting P-loss. I guess the other question is, does that really tell us the environmental impact? Because we can measure water quality, but first of all, we don't have a whole lot of monitoring of water quality. Very few sites where we're actually monitoring water quality. But the other question is it seems to me it makes a big difference if you're in Toledo, in Lake Erie, and you're in the lower Chesapeake Bay in terms of the impact of high P on water quality. Seems it's got to be.
Yeah.
So do we know, for example, what the interaction is with sediment? And I have a real concern that if one of the ways we start lowering our phosphorus index is to move away from no-till, but then we're all of a sudden going to have a lot more sediment problems. And how much does that contribute to the water quality issue?
Well,
So I guess
yeah, I think,
is P limiting? I
Yeah.
guess? Or do we know when P is limiting?
right. I think, first thing is, I'm not saying move away from no-till, okay?
No, I know you're not saying that.
And I don't think that's the answer either, because exactly what you said, and that's, they're talking about in Ohio, do we need to plow once and bury all this surface P and start over? What are the implications for erosion there? I think we need to look at different ways. For example, in Ohio, one of their practices is, in their no-till, they go out in the winter and spread phosphorus fertilizer on the surface. If they would just do like we do here and put most of their phosphorus on with their planter, they probably wouldn't have the problem. So I think there are ways, but we got to understand the situation. The other one is, you have a very valid point, and really we're back to our old friend, the Bay model. Now, this is the Bay model, not the Bay watershed model, but the one that concerns the water in the Bay, is, setting this water quality goal. What is it for a given area, given water body? I put it in here, be nice. What's the goal? We can say, what's the P index that we got to worry about? But, this is not a trivial question right here. What is that goal, and how does it vary? What are the conditions? Back to another value judgment too. What level are we willing to accept? I don't have the answer to that. I think you make a very valid point. Right now, our best that we have is the Bay water model to kind of guide, what they say is the impact of nutrients in the Bay, and we've got to keep them out of there. Best I can offer. I think it's a valid point. It is a big question.
It's counterintuitive to think of no-till increasing the water intake of the field. Now we're seeing problems with chronic disease. So is that happening? Is that model really happening throughout the year, or are they small?
A lot of times it's small peaks, and the other thing, if you look at this particular data set here of Andrews, look at the scale. We're up here, 6, and we're down here less than 1. So again, I'm not saying that no-till is bad. I think that the message here, first off, I was just using as an example. I wasn't attacking no-till, but the net effect probably is positive to no-till. I think it is. But I think we've got to understand there is this sort of secondary issue here that we've got to recognize. And like I say, I think in Ohio, they did the right thing. They went to no-till, but they did one thing wrong in how they implemented no-till. If they would have injected their phosphorus fertilizer instead of broadcasting it in the winter, I don't think they'd have had, at least the ag part of that wouldn't have been there. So I think it's understanding and making sure that our management systems we're looking at the whole thing. So I think no-till still the way to go. I just think we've got to understand there is this secondary effect. And for them, it's almost all fertilizer. So I think it would have been an easy fix if they'd have thought about it. For us, it's not quite as easy because a lot of our P is manure, and injecting all of our manure is not that practical. So we've got to look at it a little bit harder and figure out what are our answers with manure in no-till.
We're about out of time, so let's thank our speakers.